Hello. In the previous lecture, we did topology on complex plane. In today's lecture, we are going to start with an important topic, and possibly we'll use it throughout the complex analysis, that is the sequences. Okay. Uh, Probably I'll not be doing much of the uh, proof part because most of the proofs are quite similar to the ones you study in real analysis, but still I'll try my level best to deliver you as much as possible in this particular section. So sequence and series in C. Okay, so this is the name of topic, and this is a very fundamental topic. You will see that let's say whenever we will be doing, let's say, continuity, okay, so we may be using the sequential definition. So all these things are quite important, and all those who have taken at least a course on real analysis know the importance of sequence and series, and I do not need to harp more on the importance of sequences in real analysis and similar treatment. Similarly, you know that in complex analysis also this is an important topic. Okay, so as you know, as you might be aware, that what are sequences? Sequences are function from n to any particular set x. So for example, when we are talking about complex analysis, then we would be, and I think we have already done the concept of metric spaces. We've done what is an open disk, what is a closed disk, so all those things you already know. So a sequence in a C is a function from sequence in C is a function from is a function f from n to c. So basically what is happening here, we have, let's say Zn, I can denote is at some function of n. So basically here I'm going to use as an input, I'm going to use natural numbers, and I'm going to get some output in C. This particular term is often called as the nth term of the sequence. This term is often called as the nth term of the sequence. I hope it is clear to you. Okay. And we say that okay, and we say that the sequence Zn converges. We say that the sequence Zn converges to, let's say, Z, where Z belongs to set of complex number. If we say that what? That we say that Zn converges to Z, or limit Zn is equal to Z if there exists some epsilon greater than 0. If there exists an epsilon greater than 0, if if for if for epsilon greater than 0 there exists some n belongs to natural, such that Zn minus Z modulus can be made less than epsilon for all n greater than capital N. Okay, so what does it imply? See, it implies that if I'm saying that the sequence Zn limit is Z, it implies what? Zn would be converging towards Z. And what do I mean by convergence? By convergence, I mean that Zn and Z distance can be made as small as possible. Now, question is how much small and when? So I would say whatever your epsilon might be, let's say whatever your epsilon might be, depending on that, I will answer your question. So the point is that if you're saying that, let's say a desired epsilon you've given me, I'll tell you that take n greater than capital N or something, let's say n, after which Zn minus Z mod can be made less than epsilon. So you give me an epsilon, and if I give you a natural number Zn, after which the elements of the sequence and the limit, this difference, absolute difference, is less than the desired epsilon. So whatever your desired epsilon is, I can give corresponding to that epsilon. If I can give a natural number, if in this process I am always there, I can say that limit Zn is equals to Z. So this is how you define your limit of a sequence. Again, I'm saying, how do you define? See, there are elements, okay? So Z1, Z2, Z3, so on and so forth. And I'm claiming that this sequence converges towards Z. It implies what? That the sequence, element of the sequence in Z, distance can be made less than some epsilon. Means only, what is the criteria of convergence? Convergence means what? The distance of the element of the sequence and the limit should be as small as possible. Now, in mathematics, this as small as possible doesn't work. So you have to be precise. So you have to give me some epsilon. Let's say you give me an epsilon, let's say 10 to the power minus 12. Then I will say, okay, after a particular element of the sequence element, that is Zn, and the limit, this absolute difference can be made less than your desired epsilon. So after which, after some n, and obviously this n would be some function of epsilon. I hope it is clear till now. Okay, so this is how we define the um, uh, convergence. So by convergence, we actually mean that if I'm saying that limit Zn exists and it is some unique number, then we say that the sequence Zn is convergent. Then we say that the sequence Zn is convergent, and precisely it converges towards Z. And by which I mean, given epsilon greater than 0, there must exist some n belongs to natural such that Zn minus Z modulus can be made less than epsilon for all n greater than equals to capital N belongs to natural. All these things you might have done in your real analysis class, but still I'm trying to make a certain point so that you are able to understand all these things and use all these things. Another important thing is that if the limit exists, then limit must be unique. Must be unique. So if limit at all it exists, if I'm saying that sequence is convergent, then the limit must exist and it must be unique. The second thing is limit must exist and it should be unique. Okay, so limit must be unique. By which I mean that if at all it happens that limit Zn comes out to be Z and limit Zn also comes out to be W, then the sequence is convergent if Z is equal to W. Sequence is convergent if Zn is equal to W. So how do we prove it? There can be two methods. One of the methods is very fundamental. Always remember that if A minus B mod can be made less than epsilon for every epsilon greater than 0, it implies that A must be equal to B. Remember this result. Okay. So we'll use this result. Now, if Zn converges towards Z and Zn also converges towards W, then the sequence, if it is convergent, then Z must be equal to what? W. How to prove this? Let us try to find the difference between Z and W, absolute difference between Z and W. Now, already it is given that Zn converges towards Z, and it is given that Zn converges towards this thing. So I'll write that Zn minus Z mod can be made less than epsilon by 2. And I will write that Zn minus Z mod can be made less than epsilon by 2 for all n greater than equal to some n1, and I'll write for all n greater than equal to some n2. Now, for all n greater than equal to n naught, which is nothing but maximum of n1 comma n2, if I choose n naught to be maximum of n naught n1 comma n2, I can write that if I'm writing that like, so let's say I'll write this way. What I'll do, I'll play a certain trick. I'll write Z minus Zn, and then I will write Zn minus W. Now see, this modulus can be written less than equal to Zn minus Z modulus and Zn minus W. See, you have to understand this. Now this can be made less than epsilon by 2, and this also can be made less than epsilon by 2 for all n greater than equal to n naught. Belongs to natural. N naught is what? Maximum of n1 comma n2. So after n naught, which is maximum of n1 comma n2, both of these terms, Zn minus Z can also be made less than epsilon by 2, and Zn minus, sorry, W can also be made less than epsilon by 2. It implies what? It implies Z minus W can be made less than epsilon for all n greater than equal to n naught belongs to natural. And this implies that Z must be equal to. So always remember, if the limit exists, then the limit must be unique. Another geometric way of seeing to it, to this particular thing is, let us say that Z is not equal to W. Let us say that Z is not equal to W. Now, if z is not equal to, sorry, z is not equal to w, then what? Z minus w mod will not be equal to 0. And which certainly means that distance between z and w will be non-zero. And I will select an epsilon in a certain way. So I'll select epsilon to be distance of z comma w divided by 2. So I'll select epsilon to be distance of z comma w divided by 2. Now, as I did earlier, there exists some n1 comma n2 belongs to set of natural number such that such that such that Zn, the elements of the sequence Zn will be contained in an open ball centered at Z0 and epsilon. So if I'm saying that Zn converges towards Z, what does it mean? It means that Zn minus Z mod can be made less than epsilon for all n greater than equal to some n. It implies what? It implies that all the elements after n1 will be at a distance less than epsilon. So they will be contained. So all the elements after n1. So after n1 would be zn1. Sorry, I should write in a better way, otherwise we will get confused. What does it mean? So it means, I'm writing it here. What does it mean? It means that, sorry, it means that, just give me a minute. See, meanwhile, this computer hang. Okay. So basically, what does it mean? It means that after n1, the elements of the sequence, the elements of the sequence certainly will be, see, after n1, what is happening? After n1, so I can write that zn1 minus z mod will be less than epsilon. I can write that zn1 plus 1 minus z mod less than epsilon. It implies what? It implies that after n1, the elements of the sequence will be contained, in an open ball centered at z and of radius epsilon. So it implies what? It implies that after n1, the elements of for all n greater than equal to n. So after n1, all the elements of the sequence will be contained in the open ball centered at z and less and radius epsilon. This is what you mean, right? This is what is open ball centered at z and radius epsilon. Okay. Similarly, if I'm saying that Zn also converges towards W, it implies what? After N2, elements of Zn will be contained in an open disk centered at W and epsilon. And don't forget, what is your epsilon? Your epsilon is dz comma W divided by 2. That is, if this is Z and this is W, whatever be the distance of it, we'll take that and we'll do the half and also less than it. So we'll take a distance which is less than the half of the distance of Z, distance between Z and W. So we'll take epsilon. So what we have done here, we have chosen an epsilon. So remember, if I'm saying that Zn converges towards Z, then Zn must be contained in a neighborhood of Z. Zn must be contained in neighborhood of Z, and it should be irrespective of any epsilon. So I can select any epsilon. Let's say I can select any epsilon, because see, if the limit exists, then we say that given epsilon greater than 0, Zn minus Z mod can be made less than epsilon. It implies what? It itself implies that Zn must be contained in some open ball centered at Z and epsilon for any given epsilon. So for any given epsilon, it is true. For any arbitrary positive epsilon, it is true. Let epsilon be this, then it should be true for this also. So what I've done, I've taken an epsilon which is having a distance, which is having a real number, which is equals to distance d z comma w divided by 2. So basically, what I have done, I've taken an epsilon in a manner that it is less than the distance between z and w, half of the distance between z and w, and lesser than that. I hope it is clear now. Okay, so what will happen? So let's say this is half and less than half distance. So what will happen if I make let's say this is what this is. Okay, and this will be here. So open ball centered at W and epsilon. It will not intersect. Why it will not intersect? Because epsilon is what? Epsilon is less than the what you can say, less than the distance, half of the distance joining between Z and W. So this is half. You have to make a radius in a way that it is less than the half of the distance between Z and W. Why I have done so, you will come to know later on. So again, come to the point, what I have done, I have assumed that Z is not equal to W. It implies what? Z minus W mod is not equal to 0. It implies that distance of Z and W is not 0. Now what I can do, I can select an epsilon in a certain way. I can select epsilon in a certain way. And what is that epsilon? Epsilon, let epsilon be something which is less than distance of Z and W divided by 2. So what I've done, I've chosen epsilon in a certain way, which is nothing but it is Z minus W modulus divided by 2. So this is how I've chosen epsilon and less than that, less than. So for every given epsilon, if limit Zn is tends to 0, then for every given epsilon, Zn minus Z mod can be made less than epsilon, which implies that Zn must be contained in an open ball centered at Z and of radius epsilon. Okay, so I hope it is clear that if Zn is convergent and converges towards Z, then Zn, the elements of sequence must be contained in open ball centered at Z and radius epsilon. Similarly, if Zn converges towards W, what does it mean? It means that Zn must be contained in open ball containing open ball centered at W and radius epsilon, and mind this epsilon exists. Now it implies that for all n greater than equals to maximum of n1 comma n2. Okay, and let us say this, let it be equals to, let's say, n naught. What does it mean? It means that now the elements of the sequence that is Zn naught plus 1, so on and so forth, they will be contained both of them. That implies that so Z n naught, okay, just for example, I'm giving Z n naught will be contained in both the open balls. But we already know that there is no intersection between, there is no such element for given epsilon. I'll write for given epsilon greater than 0, B W comma epsilon intersection B Z comma epsilon is phi. So therefore we arrive at a contradiction. So I hope this proof you might have learned. If you have not learned, if you will not understand this proof, please mention me in the comments. I will again reiterate the proof to you. See, this is a simple proof. What I have done here, I have used proof by contradiction. And what have I done? Again, I'm reiterating. Let us say that Z is not equal to W. That implies Z minus W mod is not equal to 0. It implies that distance between Z and W is non-zero. And certainly this is, if distance is positive, so I can choose an epsilon which is less than half of the distance between Z and W. Okay. Now, if Zn converges towards Z and Zn also converges W, that implies that the elements of the sequence after some n1 and after some n2 will be contained in open ball centered at Z, and after n2, elements of Zn will be contained in open ball centered at W. Now, it implies what? After maximum of n1 comma n2, let's say n naught, all these elements will be contained where? Will be contained in the both of these open balls. It implies it will be contained in the intersection of both of these open balls. It implies that this should be non-empty. However, for the given epsilon, you can clearly see that this intersection is empty. Therefore, we arrive at a contradiction that implies Z cannot be equal to W. It implies Z has to be equal to W. So if at all limit exists, then it must be unique. This is a proof that you already have done in real analysis classes also. Now, again, we are doing the same in the complex analysis also. So, just for a sense of repetition, I've done. I'll not do time and again all these things, but just for the sake of doing it, I've done. Okay. Now, same subsequences we have studied. What is subsequences? Subsequence is a sequence only, but having restricted the set of domain. Okay, having restricted the set of domain. So simply what? Suppose, 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 Suppose Zn be a sequence of points. Suppose Zn be a sequence of points, that is complex numbers. Okay, complex numbers in C, and that Nk is a strictly increasing sequence of natural number. I'm not writing complex number, please remember, increasing sequence of natural numbers, then the sequence Znk is called as a subsequence of complex number. Is called as the subsequence of the sequence. Is called subsequence of complex number. Nahi, is subsequence of sequence Zn. Okay. I hope it is clear. So, like, let's say Z of k plus 1. This is also subsequence. Let's say Z of 2k. This is also subsequence. Let's say Z of 2k plus 1. This is also subsequence. Let us say Z of 2k power k. This is also subsequence. All these are subsequences. I hope it is clear. Okay. And see, here I have not defined, most possibly we are not going to define something called as monotonically increasing sequence, monotonically decreasing sequence. Why? Because we have already understood this concept that uh, that the complex number actually lack ordering in the way in the similar way to that of real numbers. So this is something that you have to remember. Okay, one thing I need actually I forgot to mention previously also, that there is something called as the lexicographic, or what you can say, lexicographic order in C. So just note here. Remember what I've told, that in complex numbers in C, there is a lack of ordering like we have in R. Okay, in that sense, we do not have a ordering. Okay, so okay, so in that sense, what you can say, there is a lack of ordering like we have in C, but somehow some sense of ordering can be done, and that sense is sometimes referred to as the lexicographic. I should write it here itself so that you don't get confused. Lexicographic order in C. There is some sense of ordering which is called as a lexicographic order in C. So how do we define that? Let's say if I'm saying that Z1 is less than Z2, then lexicographic order is defined in this way. If Z1 is less than Z2, it can be Z1 can be less than Z2 only if either you compare the real part, that is real Z1 is less than real Z2, or real Z1 becomes equal to real Z2 and imaginary Z1 is less than imaginary Z2. Okay, so okay, so basically this is referred to as the lexicographic order in C. Overall, we cannot write. So we can compare the real parts, either compare the real parts, or if the real parts are equal, then we can compare the imaginary parts. So this is how we can do. However, this is this in true sense is, you can say that this is a partial order. Basically, this is nothing but this is a partial order in C. I hope you might know what is partial order. If you don't know, then please say in the comment section. I'll explain all those things. But okay, so there is a sense of partial order in C. Okay, do understand that this is something called as a lexicographic order in C. Otherwise, one has to remember that there is a lack of ordering like we have on R. So therefore, you won't find the definitions like increasing sequence or decreasing sequence, like such definitions that we had in what you say in real analysis. Although we'll have something called as Cauchy sequences and all those things. So don't worry about that. But okay, so I hope I've made my point clear here. And this I did because possibly in interview somebody may ask you, if not in exam. Okay, now let us say till now we have already seen what is a sequence in what is sequence Zn. Now if let Zn be a sequence belonging to C. Okay, so let Zn be a sequence in C. And if I say that Zn converges towards Z, what does it imply? Then it implies that, or I can say that Zn converges to Z if and only if both real parts and the imaginary parts converges. If and only if, if only if real part of Zn converges towards the real part of Z, and imaginary part of Zn converges toward imaginary part of Z. Okay, so always remember that if the sequence Zn is convergent, then so therefore at times you see if you're well aware with R square, or if you're well aware with real analysis in R also, then I don't think there is a problem with a complex analysis. So remember this particular fact, that if Zn be a sequence in C, then Zn converges towards Z if and only if real part of Zn converges towards real part of Z, and imaginary part of Zn converges towards imaginary part of Z. And it is quite easy to prove, what you can say. Let Zn be convergent towards Z. It implies, then we know that real part of Zn uh, and minus real part of Z, we want to compare this. I mean, we want to know this, and this is equal to real part of Zn minus Zn modulus. And certainly we know that real part of Z is less than equal to this. So we know that real part of Z modulus is always less than equal to modulus of Z. This is something that we already know. And if Zn converges towards Z, it implies what? This can be made less than epsilon. It implies that real part of Zn converges towards, real part of Zn converges towards real part of Z. And similarly, you can do for the same imaginary part of Zn. Similarly, you can prove this. I'm leaving up to you. Imaginary part of Zn also converges towards imaginary part of Z. Now, because since if and only if condition is there, conversely, what you can suppose? Conversely, suppose that real part of Zn converges towards Z. Real part of Z, and imaginary part of Zn always also converges towards imaginary part of Z. Then let us think about this. Let us think about Zn minus Z modulus. And obviously, because Zn is what? So it will, I can write this as less than equal to real part of Zn minus real part of Z modulus, and plus imaginary part of Zn minus imaginary part of Z modulus. I think this is quite evident. You know already that so you already know now this particular thing, that what I can write this, I can write at Zn, I can write it as real part of Zn plus iota imaginary part of Zn minus real part of Zn, real part of Z plus iota imaginary part of Z. Okay, and then I can write real part of Zn minus Z, real part of Z, and then I can write it as plus iota outside imaginary part of Zn minus imaginary part of Z, and this whole modulus. And then certainly I can write less than real part of Zn minus real part of Z. By triangles inequality, we know that, and this iota mod is 1, imaginary Zn minus. So I think some steps, if I leave also, kindly do it on your own. So Zn minus Z modulus can be made less than equal to real Zn minus real Z mod plus imaginary Zn minus imaginary Zn mod. So already I know that if real Zn tends to real Z, so it can be made less than epsilon by 2. Similarly, it can also be made less than epsilon by 2. It implies that Zn minus Z modulus can be made less than epsilon by 2 for all n greater than equal to some n naught belongs to natural. It implies what? It implies limit Zn is equal to Z. So we took limit Zn equal to Z, and we have proven that individually real part of Zn converges towards real Z, and imaginary part of Zn converges towards imaginary Z. And also conversely, we have supposed that real part of Zn, if it converges towards real Z, and imaginary part of Zn, if it converges towards imaginary Z, then Zn also converges towards Z, and it proves our point. I hope it is clear now. So for example, one of the examples you can take this way. So let Zn be equals to 1 upon n plus iota n minus 1 upon n. Clearly, we know that the Zn converges towards iota. So definitely Zn, the real part of Zn here converges towards what? 0. We know that the real part of Zn converges 0, and imaginary part of Zn obviously converges towards 1. You know that imaginary part of Zn which would converge towards 1. And so therefore we know that limit Zn converges towards what? Iota. Okay, I hope it is clear. If the sequence is not convergent, then we say that sequence is divergent. That is, if we say that the sequence Zn minus Z mod cannot be made less than epsilon for all n greater than equal to some n naught belongs to natural, we if it cannot be made less than epsilon, or we can say that if the sequence does not converge, if the sequence does not converge, let's say the tendency is not unique, if the sequence does not converge, then we say that sequence diverges. Then it implies that sequence Zn. For example, one of the very standard example in complex analysis is to discuss the sequence minus 1 whole raised to power n. And in complex analysis, we'll discuss some sequence called as iota raised to power n. And we know that if I take, it will be equal to 1 if n is equal to 4, 8, 12, so on and so forth. And it will be equals to iota if you know that if I this is the case, then it will be iota. So I'll write that if k is equal to 4n, then it is equal to 1. If k is equal to 4n plus 3, then it is equal to iota. No, no. If it is equal to 4n plus 1, sorry. If it is equal to 4n plus 1, then it is iota, and it will be equals to minus 1 if it is k is equal to 4n plus 2, and it will be equals to minus iota, sorry, if k is equal to 4n plus 3. I think this is something that you already know from your standard 11. And so we can write it in as well as in this manner, that iota raised to power n would be nothing but it is equal to 1 if we take n such that it is 0 modulo 4. Okay, and it will be equals to iota if n is 1 modulo 4. Similarly, is 2 modulo 4. So it will be, I think, minus 1. And then you can write minus iota. So it will be, I hope it is quite clear to you. So clearly, we know that it implies that the sequence iota raised to power n is a divergent sequence, not a convergent sequence. Okay, it is not a convergent sequence. I hope it is clear. So okay, I hope it is clear. Okay. Okay. So next we have boundedness of a sequence. So sequence Zn in C is said to be bounded if there exists m greater than 0 such that Zn modulus is less than m for all n belongs to natural. So this is when we can write that your sequence Zn is bounded. So if sequence Zn is said to be bounded, if Zn mod can be made less than m for all n belongs to natural. I hope it is clear. Okay, so this is boundedness. Now, a little bit more about limits only. So we have seen that if a limit exists, then the sequence is said to be convergent. If limit doesn't exist, the sequence is said to be bounded. If Zn modulus is less than m, For all n belongs to natural, the sequence is said to be convergent. Now just think about this sequence. What do you think about this sequence? Just think about this sequence. What do you really think about this sequence? Argument, this is I'm writing principal argument, minus 1 raised to power n divided by n. What do you think that this particular sequence? So I'll write something here. I'll write Zn here. What do you think about this sequence? Is it a convergent sequence or is it a divergent sequence? How do you think this would be used? So let's say if I place n equals to 1, it implies argument of minus 1, which is certainly pi. If I take n equals to 2, then argument will be equals to what? Argument will be simply, I think, 1 over 2, and argument of 1 over 2 will be 0 because positive side. So this is principal argument, mind you. Okay. Now, if you take real and positive, then it is 0. And if you take real and negative, then it is pi. So, and now if you take n equals to 3, then argument of, I think, minus 1 upon 3 would be simply pi. So clearly, if I write this sequence Zn, it is having a non-unique tendency. So basically, again, this particular sequence is a divergent sequence. Divergent sequence. So this is a divergent sequence. So I hope you might have got this, all these things regards divergence and convergence. And one has to understand all these things. I mean, these are not difficult concepts, but you can, I mean, these are all concepts that you have already done in your standard, real analysis courses. Okay. Let's say if I give another example to you, let's say, what do you think about this sequence? Zn is equal to iota raised to power n was divergent, but if I divided it by n, then what? Then we know that Zn minus 0 mod, I'm claiming that the limit to this Zn, the sequence Zn would be 0. So let me see that whether my claim is right or not. Zn minus 0 mod means what? Iota raised to power n mod divided by n, and it is equals to 1 over n. So it can be made less than epsilon for all n greater than equal to some natural number. It implies what? It implies that limit Zn is equal to 0. So clearly, you know that iota raised to power n, this particular sequence is a divergent sequence. However, if you take another sequence, which is, let's say, Zn dash, which is iota raised to power n divided by n, then this definitely converges and converges towards 0. So I hope all these things you might have done in your real analysis class also. And so I hope all these things you should be knowing. So I'm not concerning much, but still, I really want you to really understand all these things. A few things I'm going to write without proof, and one of them is the algebra of limits. So one of them is algebra of limits. So this is something that I'm going to write without proof. I hope you might get the proofs in the book itself somewhere. So algebra on limits. So let Zn and Wn be the sequences in C. Let Zn and Wn be sequences in C. Be sequences in C. And let us assume that limit Zn converges towards Z and limit Wn converges towards, Wn converges towards W. Then the following holds true. That is limit Zn plus Wn, this converts towards Z plus W. Then limit Zn into Wn, this converts towards Z into W. Then limit, and let's say if I multiply with alpha, where alpha is some complex number, this converges towards alpha into Z. Okay, one of the very important topic I think everybody knows, but still I would recommend you to prove it, that the set of all convergence sequences, I think all these properties are written. I think you can prove it on your own if you have a little bit of understanding of vector spaces, I'm directly writing. I've given you enough hint. You can use these two hints, and you know that the zero sequence is always convergent. If Zn is convergent, then limit minus Zn would be let's say if the sequence Zn is convergent, then minus Zn would be convergent. You know that the sequence 0 is convergent. You already know that limit alpha Zn converges towards alpha Z, and you know all these properties above. If you use all these property and the definition for the vector spaces, you'll get one of the important results, that is set of all convergence sequences in C forms a vector space over C. Forms a vector space. I think over C I should write. Okay, over C. I hope this is clear. Another important hypothesis is, let's say if another important hypothesis is that assume that limit Wn converges towards W and W is non-zero, then obviously there exists some n belongs to natural such that Wn would be non-zero. So what does it mean? It means that if W is non-zero, let's say if W is positive, then see Wn minus W mod can be made less than epsilon. And let's say take epsilon to be equals to W upon 2. It implies what? It implies Wn minus W can be made less than W by 2. It implies that Wn lies between W by 2 and 3W by 2. It implies what? It implies that for some natural number n, Wn would be always greater than 0. Similarly, you can prove a negative number. In general, remember that if limit Wn is equal to W and W is non-zero, then there would always exist a tail of a sequence which is non-zero. And this gives another proof, this gives us another motivation that if this is the condition, that if Wn converges towards W, which is non-zero, then limit Zn divided by Wn will converge towards Z upon W. So all these things are called as the algebra on limits. I hope this you might have done a lot many times, so I will not concern myself great to a great deal with this. In the next lecture, we are going to do something called as the Cauchy sequences, and then we'll move to the series part. Series, I hope I'm going to do in real analysis also. I hope you might have done in real analysis to some level extent. And this sums up our lecture first on sequences of complex numbers. Till then, take care. We'll meet in the next lecture with Cauchy sequences, definition for Cauchy sequences, a little bit about limit inferior and superior, and then possibly we'll do a few questions and then we'll go towards the series part. So I hope you might have learned all these things. And in series also, we are not going to concern much towards with respect to the proof of the test. We are going to just use the test, that is like comparison test. You know all these things from your real analysis class. I'm not going to prove it, but directly write the results. So all these things you have to keep in mind before starting the complex analysis. So I hope you are going to keep patience. You keep bearing with me. Till then, take care.